great pleasure to have Fabio Anza as a speaker today. So Fabio is not an unknown face to Palermo because he got his degree from here before moving to Pisa and then Oxford, where working under the supervision of Latko Vedrali, got his PhD in 2018. Immediately after, or shortly after getting his PhD, he started a fellowship funded by the Templeton Foundation at the University of California, Davis, under James Crutchfield. And then, say in 2021, he joined Incubator for Quantum Simulations in Washington before moving to Trieste later on, where he stayed shortly until in 2024 he was appointed as say an associate professor at University of Maryland. Fabio is looking into aspects of the interplay between statistical mechanics, quantum information, mathematical physics, but also, and that's probably something that say is closest to the sort of things that I do, for instance. And also is interested in gravitational physics and the interplay with information. So Fabio spoke already 1 year ago, or nearly 1 year ago. So this is becoming a sort of regular update on the progress of his research, and it's a great pleasure to have him. So Fabio, the stage is yours.
Thank you so much, Mauro, and thanks guys for coming in. So actually, last year I spoke about observable statistical mechanics, which is kind of a trend about the foundations of thermization and statistical mechanics. I'm not going to talk about progress in that direction. Rather, today I'm going to talk about basically what came out of my postdoc with Jim Crutchfield in Davis, which is kind of a way to formulate quantum mechanics in a way that it allows me to use dynamical systems theory and its tools to study open quantum systems. So I'm gonna, I hope, let me see. All right, so I don't see anyone, so I don't see faces or anything. So if people have questions or anything, just unmute yourself, because the only thing I see is my own screen. So just let me know if this is okay, and I can start the presentation.
Okay.
All right, thanks. All right, kinetic theory of quantum information transport. So this is a way for me to essentially use the tools from classical transport theory in conjunction with geometric quantum mechanics to study the dynamics of ensembles in quantum systems. And what I mean by that, it'll be the whole topic of the talk. But let me just start with a kind of what my long-term goal is, which is to basically understand in a principal and mechanistic way how many body quantum systems that interact with highly structured environments, so environment that kind of actively operate on the system in a non-trivial way, basically store and process information and other resources like energy, matter, or something else. So that's kind of the broad understanding you should have this. There's 3 parts of this talk. The first one is geometric quantum mechanics. The second part is going to be how to use geometric quantum mechanics for open quantum systems. And the third part will be about the dynamics. So the first part, I'll kind of go quickly because I'm guessing that some of you already had some exposure to it, but I think it's important to give some sort of a shared language. Then the second and third part are going to be the kind of truly semi-novel. It's been a couple of years now, part of the talk. All right, so what is geometric quantum mechanics? We start from Dirac's quantum mechanics, the usual third year stuff. There's three pillars: states, vectors in Hilbert space, observables, self-adjoint operators, and dynamics. The most obvious dynamics is Schrödinger's equation. Then, of course, we have open quantum systems, but we can always think about an open quantum systems as a small part of a larger unitary thing. So Schrödinger's dynamics will do for now. So we have these three objects, and what we're going to do is that we're going to look at these three of them from the standard picture into geometric quantum mechanics. So why we want to do geometric quantum mechanics? The idea, the starting point is that there is two descriptive redundancies which are well known. The first one is the phase and actually the overall normalization of a state, which is not physical in the sense that when we do expectation values, these things don't matter. And so the Hilbert space description is redundant in terms of phases and overall normalization. And the second one is that when we write a density matrix, we usually write it in terms of the diagonal ensemble, so eigenvalues and eigenstates. But that's not the only way you can do it. And in fact, there's an infinite number of ways in which you can do that. But allegedly, let's say, you have no way of telling the difference between these two different ensembles as long as you make measurements only on your system. But we'll see that the situation is kind of slightly more, while the statement is technically true and physically true, which is an important part of quantum mechanics, the situation is a little bit more complex than that. But there is these two descriptive redundancies, and we can get rid of these descriptive redundancies by going into geometric quantum mechanics, which is kind of at a colloquial level. The way you can think about it is that rather than thinking about states in terms of vector, you can think of them in terms of locations on a manifold. So what's the address, right? If I want to tell you where to go, I can give you kind of the vector that points from where I am to where I want to go, or I can give you a set of coordinates where you need to go. So that's the geometric perspective. So starting point, as always, we have a, let's say for now, finite dimensional Hilbert space, dimension D. And actually, let me see if I can, yes, pointer option. Where's a pointer? This should be better, yes. Finite dimensional Hilbert space, we have a bunch of complex coefficients, zk. They belong to the complex numbers, and of course we normalize them to up to some lambda, which has to be positive and non-negative. And of course, if we multiply all of them by a phase, we get the same physical state, but of course we get a different vector. And this is true also for normalization. So in general, if I take a Hilbert space vector and I multiply it by and I multiply all the components by a complex number, I get a different vector, but it's the same physical state. So that's the descriptive redundancy. We can get rid of this by going into the complex projective space. So what does this mean and what does that entail? I'm not going to go through the math. If you guys are interested in the math, please do stop me, and I can be more specific on the math or on parts of this. But I'm just going to go through this quickly. So we'll look at states, observable, and dynamics from both the standard and the geometric perspective. So as I said, vectors in Hilbert space is the standard approach. Instead, we're going to think in terms of points on a manifold. And the manifold is called a complex projective manifold. For the math-oriented people, this is a Kähler manifold, which means that it has two notions of geometry that are kind of intertwined with each other. One of them is Riemannian, which is about length, areas, volumes, and things like that. The other one is symplectic geometry, which is in fact the geometry of a classical phase space. And we're going to use that because this is going to be extremely important, because one of the most important points is that as physicists, we get trained a lot on classical mechanics and Hamiltonian dynamics and Lagrangian dynamics, which are really the modern formulation of all of that is symplectic geometry. So our intuition, whether we're knowingly or unknowingly, our intuition works really well when we are trying to understand things that live in a symplectic space, which also quantum systems are. Right, so a particularly important set of coordinates are probabilities and phases. So if I take my complex coefficient, I take the modulus. That's positive, and they all the square sum to 1, and there's phases, right? So we have the pk and we have the phi k, and these are going to be really important for geometric reasons, but of course they're very important for practical reasons in the sense that they entail a choice of a basis, of course, and then once you choose a basis, the pk are basically everything. They contain everything that we can hope to know. As long as we limit ourselves to a particular basis. They're, if you will, the diagonal element of a density matrix when written in that basis. And the phases, we don't have access to it. If we want to have access to the phases, we have to change basis, measure the diagonal matrix elements, and then do a reconstruction. Good. So you already know some of this. Of course, for a qubit, the block sphere coordinates, theta and phi, are the ones that actually realize the complex projective space, because, and this is CP1, right? Complex CP projective 1, dimension 1, because the dimension of the complex projective space is 1 less than the dimension of the Hilbert space. Theta and phi are your coordinates, and they're very important because they're the natural, they codify the natural notion of distance, the Fubini study distance between two points. Very good. As I said, there's another particular set of coordinates, which are probabilities and phases. I haven't said why they're important. We'll look at this in a moment. But effectively, when you represent things in terms of probabilities and phases, it's more useful to think of it as a square, not because geometrically they are a square, because you haven't changed anything, right? Geometry is an intrinsic property, so this is just a representational tool. But because when you think about probability distributions, which is something that we'll have to do if we want to deal with open quantum systems, it's more natural to use probabilities and phases for geometric and actually measurement-based reasons. Good. So CPD minus 1, it's a Kähler space, as I mentioned. On the right-hand side, you see there's a notion of Riemannian geometry, which is your usual, if you will, general relativity geometry. On the left-hand side, we have symplectic geometry, which, if you will, is the fact that you have canonically conjugated coordinates, or in other words, it's the fact that the notion of canonically conjugated coordinates exists, and it's kind of unique in the whole space. And P and phi, as you can see, are particularly important because they diagonalize what it's called the symplectic two form, or in a more familiar, possibly more familiar language, the Poisson brackets, right? Pi, phi, j are a little bit like xi, pj, position and momentum in our favorite phase space. The Poisson brackets of P of xi pj momentum is delta ij. In the same way, the Poisson bracket between probability I and phase j is a delta ij. All right, so we go from vectors in Hilbert space to points in a quantum phase space, and I'm going to start using quantum phase space, and kind of, to me, what gives legitimacy to this nomenclature is the fact that there exists actually a notion of symplectic geometry. So it is indeed a phase space in the usual way, at least mathematically. The main difference with the standard phase space is there's two main differences. One is the global topology is compact, so it's finite, like the block sphere. And the second one is that it's curved, right? The geometry is not flat. The core notion of metric for quantum states is called the Fubini study metric. This is not important right now, but the way you should think about it is that this is related to the notion of fidelity. Essentially, when you're trying to understand, when you're asking the question how far two quantum states are in the sense of the Fubini study metric, what you're really asking is how distinguishable are these states by means of quantum measurements. And then you get back to the usual construction of distance between quantum states with the trace distance and the Fubini-Studi distance, and which are related to the overlap, to the modulo square of the overlap between two states.
All right. So what are
observables in this picture? You start from your favorite self-adjoint operators, which in finite dimensions is just Hermitian. And then basically what you do is that you coordinatize the notion of state,
as in
Z, that's your coordinate in the complex projective space. And then, of course, the operator O defines a Hermitian form, which is just the expectation value, the normalized expectation value that you see in this on the right hand. And that's your notion of observable. So the way you should think about it is that they are functions from the manifold of states to the real numbers. And they're particular function because they have to be, of course, they have to be self-adjoint forms. And if we write, for example, an observable on a qubit in the p phi coordinate, this is how it looks like. There's p O00, 1 minus p O11, which are the diagonal matrix elements, and then the off diagonal contains coherence in the phase phi times some square root of p 1 minus p. So observables are pretty much like observables in a phase space. They are just functions from the phase space to the real numbers, just a particular kind of observables.
This is how they look
like in p phi coordinates, the three core observables of a qubit, sigma x on the left, sigma y in the middle, and sigma z in the right.
So they're the
functions. An important aspect is what is the algebra. This is really, again, it kind of confers on the legitimacy of calling this a quantum phase space, is that the usual algebra of observables is the algebra of Hermitian observables with the law. It's a Lie algebra because we're using the commutator. And that means that if I have A and B, which are Hermitian or self-adjoint operator, and I do minus I commutator between A and B, I get, again, an observable. So the law is that if I do commutator times minus I get, again, an observable. Now, on the geometric side, the commutator is represented by the Poisson bracket. So if I have two functions, fa and fb, which each represent the observable A and the observable B, then I do the Poisson bracket between them, I get a third function, and that third function, fc, is the observable that represents the self-adjoint operator C at the level of Dirac's quantum mechanics, so to speak. So the algebra is a Poisson bracket algebra. Again, exactly like in classical mechanics. So self-adjoint operators get mapped into Hermitian projective functions which have a Poisson algebra.
Dynamic. Third part.
So of course we have Schrödinger. The easiest way to kind of convey this point is that you take Schrödinger's equation and you compute the expectation value, the dynamical expectation value of an observable A, and this is the equation that you get. But of course, this is a relation between observables, and we already said that the algebra of observables through the commutators gets mapped into the algebra of Poisson brackets. So we get an equation that represents the dynamics, which, surprise, surprise, looks exactly like Hamilton's equation of motion. The derivative of an observable is the Poisson bracket of that observable with the function that represents the Hamiltonian. So this is exactly, if you will, Hamilton's equations of motion, just in this particular space. So Schrödinger's equation gets mapped into Hamilton's equations of motion, and this is particularly kind of suggestive in the p phi coordinates because they diagonalize this simplicity to form. I heard a blip.
Yeah, can I ask you a question? Just a curiosity.
Yeah, sure.
So
absolutely.
I'm familiar in the continuous variable regime with the Wigner function formulation of quantum mechanics, for example. How is this related? Because in that setting, the dynamics is not Poissonian. You have the Moyel brackets instead of the Poisson brackets. How do these things kind of reconcile?
It's a different
representation. So there's not really a direct connection as far as I know.
Yeah.
Okay, so they are just different things. Okay.
Yeah.
So the way I think about it, so I gave you a math answer. Let me give you the physics answer. They kind of, to me, they are different representations of quantum states, but they kind of operate at different levels. This is a completely faithful representation in the sense that if I think about the block sphere and the kind of most naive dynamics, right? I have a rotation, I have a point that rotates, right?
This is just
you can describe this with a vector Hilbert space thing, or you can describe this with Hamilton's equations of motion with a certain Hamiltonian. But they are, in fact, everything that you're describing is the geometry of the dynamics, right? You're saying the dynamics occurs on a line, in this case, something that you would call an attractor. In general, it doesn't have to be an attractor, it's just the line, the dynamic, the trajectory, and you're describing the geometry of that trajectory.
Okay.
That's the whole point.
Okay. No, perfectly reasonable. But so you can do this construction for continuous variable systems?
Yeah.
Okay. So the way this would work for continuous variable systems, think about psi of x, like Schrödinger. Schrödinger's equation, like the old one for like particle in a box, or what's your favorite model, right? You take your psi of x, you write your psi of x as a square root of p of x e to the I phi of x, and then what you have is Poisson bracket p of x phi of y is delta x minus y.
Okay, great.
So basically, the mapping, it's more like you're going from a finite set of coordinates of or into an infinite set of coordinates, which is a field, if you will.
Okay, thank you very much.
So just to
kind of
finish this point,
the Wigner function there is just a
way to
represent
quantum
states
in a way
that it's as analogous as possible to a phase space.
This is not what we're
doing. What we're doing is actually saying that underneath the quantum Hilbert space, there's a notion of quantum phase space because of the geometry that quantum states have. While what Wigner functions do is that they take your quantum state, they do some kind of projection mapping it into an x and p space, and then you look at the function that operates that projection as a function of x and p. So to me, they're like, they just operate in different spaces.
Okay, very clear, very interesting. Thank you.
Sure. And
I didn't say this, but please do stop me whenever you want and ask me questions. And this is, I'd love for this to be a discussion.
All right, so
Schrödinger's and Hamilton are kind of dual to each other in the way that we just discussed. So what happens in open quantum systems? That's the main, that's kind of why we're here. So geometric quantum mechanics for open quantum systems, how do we do it? We need a notion of geometric quantum state, which is just a probability measure on the manifold of quantum states. And this is kind of, if you don't want to kind of pay attention at the math, just think naively, I have a bunch of coordinates and they're in a phase space, and I'm doing classical mechanics, and I need to use probability distributions because what represents the knowledge that I have about the state is not a single point that moves in the phase space, but it's a probability distribution that does something in that phase, in that state space. So what do I need? I just need to put probability distribution on the same space, on the same phase space. And this is exactly what we're doing. We're just kind of being careful with the math. So the math that you actually need is measure theory on a manifold, which sounds a bit fancier than it actually is, because it's just probability theory on canonically conjugated coordinates. You just have to remember sometimes that the space is not flat, it's curved, so you need to add a g mu nu here and there to have things that are consistent.
So
how do you build this, like from a principled perspective? And the idea, this is the physical part. So I'm gonna
take a second
to clarify this. The idea is the following. In open quantum systems, we think we have density matrices, and the reason why we have density matrices is because our system is part of a larger system. So what describes the statistics of my system is a partial trace of a pure state. So in a certain sense, what determines my state, the state of my system, is the global state of the joint system and environment. However, when you do a partial trace, you literally erase all the information about the environment. That's the whole point of doing a marginal.
So it is a bit
hard. So that representation of the state of a quantum system does not contain any information about how that density matrix was created from the globally pure state, right? It's a partial trace, so you're literally erasing by averaging. So the question that I'm asking, because I want to go a little bit beyond the usual density matrix-based formulas, is what is the actual, how does the environment determine the probability measure on the manifold of quantum states? And what you're going to see is that the notion at which we are operating, so the interpretation of our notion of geometric quantum state, is not as a density matrix, but it's actually as a probability distribution of pure states. So it's the ensemble behind the density matrix. Now, of course, from that, you can always compute the density matrix, and that codifies everything you can ever hope to measure on your system. However, that information, that representation, the distribution of pure state, it's actually richer than just the density matrix. And we'll look at all of this now in a more principled way. So how do we build these objects? We start with our favorite bipartite splitting of our universe, quote unquote. There's a system, there's an environment, tensor product. The way we usually do, we write the globally pure state in a tensor product basis. The A, J are for the system, the E alpha are for the environment. And we rewrite this is just linear algebra, as a sum over alphas. Something you can always do just by defining your P alpha and your chi alpha in this way. But there are two comments on this. The first one is that, of course, you're going to be familiar with the Schmidt decomposition. This looks a lot like the Schmidt decomposition, but it's actually kind of the opposite of that, because the Schmidt decomposition goes from, it runs over the dimensionality of the system. This runs over the dimensionality of the environment. However, there is a way to make this equivalent to the Schmidt decomposition, and we might get the time to talk about it. So what is the interpretation of P alpha and chi alpha? Is that once you do a projection on E alpha, right? You get, if you imagine that you measure your environment and you get alpha equal 42, then as a result of you observing the environment, the state, the conditional state of your system will be the state chi 42. So the idea of these decomposition of the globally pure state is to extract conditional probability distribution. So given that the environment is in some state E alpha, then the state of my system is some chi alpha, and this happens with a probability P alpha.
Right. So how do you
represent this state of affairs? You get a probability distribution, you get a probability measure where, again, there's a sum over alpha, P alpha, and delta chi alpha. And delta chi alpha is just the Dirac measure, right? So if you think about it on the sphere, on the block sphere, you can imagine that you just have a bunch of points on the block sphere all over the place, each carrying with it kind of a backpack of probability, of a certain probability mass, P alpha.
Good.
The interpretation is as an ensemble in phase space. So I kind of anticipated that, but I'm going to reiterate it, because when you look at it, through probabilities and phases, this acquires a very much like a classical flavor, because what you're doing is, well, you have ensembles of canonically conjugated coordinates in a phase space. So this is very much like classical StatMech, just using probabilities and phases instead of position and momenta, and then you end up into the quantum state space, but you have to remember that your state space is not flat, it's curved.
Sorry, can I ask a quick question? On the previous slide, so those states, so this chi alpha, E alpha are orthogonal or not in this?
The E alpha?
So in this representation, the E alpha are a basis, so that this, you can always do that. However, they're a basis of your choice. Yes, they're orthonormal basis. The chi alpha are not.
Okay, so that's why it's not actually decomposition then, okay.
Correct. Now, the choice
of E alpha, of course, is up to you.
So, I can
choose the E alpha to be the Schmidt partners of the Schmidt states.
I can always do that. The Schmidt partners
are orthonormal, however, they're not a basis because there's not enough of them, right? So as long as I choose, for example, the first ds of these vectors to be the Schmidt partners, then this is going to be also the Schmidt decompositions. So if you want, one way you can think about this is that the basis that you choose to look at the environment is like a knob that you can adjust. In general, it's going to be an orthonormal basis, right? And it is what it is, fine. Or you can choose the Schmidt partners, and then this decomposition turns into the Schmidt decomposition. However, in between, you get all sorts of like choices, right? That they're up to you. So if you will, for me, this is actually the realization that when we take the density matrix, we diagonalize and we look at the Schmidt vectors as the eigenvectors of my reduced density matrix, we are implicitly conditioning on the environment in a specific way. We just have a way to do it just by looking at the system, which is something that usually, like if you do this in classical probability theory, you cannot, it doesn't happen, doesn't work out in the same way.
Okay, but then I don't quite see the connection between these two things you said. Like, okay, in this representation, you're essentially describing what you, like, if I choose to use a specific measurement on the environment, then this chi alpha will be the conditional states, that's fine. And p alpha, the probabilities. Then the density matrix thing, when you diagonalize, it's a bit different, no? Because
so what you're gonna get, because of the fact that the alpha are orthogonal, that's orthonormal. Basically, when you do a partial trace, the density matrix is going to be sum over alpha, p alpha, chi alpha, chi alpha.
Yes, like you'll get a different realization in terms of rank 1 projectors. Right. Which will not be orthogonal in general, so will not be a diagonalization in general.
Exactly. Right. However,
if for the E alpha you do choose the Schmidt partners,
then it's a diagonalization. Yes.
So that's the connection.
That's what I wanted. My point is that the basis that you choose on the environment for this to work, it's completely up to you. It's like a gauge. It's something that you choose.
So you're saying to think of density matrices directly in from the purification. That's kind of the
right. That's the flip side. This is the other side, right? You can. If I did this starting from the density matrix and not starting from the globally pure state, what I would have said is take a density matrix, diagonalize it, then purify it. You get basically a Schmidt decomposition in the globally pure state. Or instead of taking eigenvalues and eigenvectors, I can choose another probability distribution of pure states and purify that one.
Yes. Yeah.
Make sense?
Yes.
All right. So, ensembles in phase space. Right, the interpretation
is the probabilistic one, right? You have a probability distribution that your system will have a conditional state in a certain region. So it's an ensemble.
the most naive
and kind of obvious one is that you take your block sphere and you use your calculus to do probability distribution on the sphere, and the probability distribution on the sphere is going to be a geometric quantum state. And there's a little bit of a mathematical kind of nuance, because if it's continuous, you're going to have a probability density. If it's not in general, you just have a measure. But these are kind of mathematical details that don't change the underlying physics. Now, the advantage of PM5 and what I was saying at the beginning is that when you look at the measure, at the volume measure, the ones that we use to do integrals from the PM5 coordinates, it's a flat measure. So really, as long as we are thinking in terms of probability distributions, and not necessarily in terms of distance between points, then probability and basis coordinates give you a volume which is exactly like the phase space volume that we would use, dx dp, right? There is a normalization of 1/2, but you can always take that away with slightly different choices of normalization, and that's kind of physically inconsequential. So this looks very much like classical StatMech. That's again, I'm making this point over and over because I wanted to be clear. So connection with the density matrix, we kind of touch on that, but the generic thing is that you take your homogeneous coordinates z and z bar, z bar I and z j, and you do an average. And the average, if this is your measure, then the average is just basically the average of a cat paired with its bra, and that's just a generic decomposition of your density matrix. So as you can see, basically the measure, of course, being an ensemble, comes before that. All right. So interpretation. So here's a thought experiment that I used to think about this. On the left-hand side, you got situation A, right? You have two bags of quantum states. They are, or of qubit states, they're orthogonal, 0 and 1. So north and south pole on the block sphere. How do I choose between them? I flip a coin that's a bias coin, and the bias is some lambda, right? So with a probability 1 plus lambda over 2, I take a state from the 0. With a probability 1 minus lambda over 2, I take a state from a 1. I do this many times. I get my statistics. On average, how are my expectation values described? With the density matrix, that is, of course, diagonal. 1 plus lambda over 2, 0. 1 minus lambda over 2, 1. Left-hand side. Right-hand side, the game is exactly the same. The only difference is that now the coin that I use, it's a fair coin. So 1/2 head, 1/2 tail. However, the quantum states that are inside the boxes that I use, they are not orthogonal, right? So I have a probability of confusing one for the other. And to just drive home the point, I just choose this particular set of two states. The actual specifics of the details are not important. They're just chosen so that the overall density matrix you get, it's exactly the same as in situation A. All right, so here, what I have is two physically, clearly very different situations, right? However, they're built to give me the same expectation, but the same density matrix. And so if I measure things on the statistics of states that I get exactly the same result. So I have no way of telling them apart. If I put situation A in Mauro's office and situation B in my office in Maryland, and we talk about this, there's no way we can tell them, we can tell these two situations apart, right? So I would have no way of knowing that Mauro used situation A while I use situation B. It's just, it's not possible. However, physically, there's a sense in which these two are different situations, right? And the interpretation to me is that what happened is that we use different resources to create the same statistics. And on the left-hand side, you can think of lambda as a resource because it's a bias. Of course, if lambda is 1, I have the fair situation. If lambda is 1 or minus 1, I have the completely biased situation. So on the left-hand side, the bias has a classical nature, right? My coin is not fair. On the right-hand side, the source of the bias is not classical, it's completely quantum because it's the non-orthogonality between the states that are inside the boxes. So what Mauro did in using situation A is using a classical source of bias, while what I did in situation B is using a quantum source of bias. Now, from the density matrix perspective, these two situations are exactly one and the same. However, from the perspective of the ensemble of pure states that you get, the situation, of course, is very different, because in Mauro's case, you're going to have 1 plus lambda over 2 and 1 minus lambda over 2, north and south pole of the block sphere. While in my case, I'm typically going to get something, for example, on the left and the right side at the right height.
So the geometric quantum
state, which is the probability measure that is different in these two cases, contains effectively the information about how the correlations between system and environment determine the measurement statistics of our system. So the measurement statistic can still be the same. However, it was created in a different way. So in a certain sense, these two experiments landed on the same measurement statistic, but they use different resources. So this
Sorry, before you, can you clarify what do you mean by bias in the other slide? Because maybe
I just
there's a difference between the eigenvalues, or no?
Yeah,
Okay.
Yeah, it's literally
so P0 minus P1 is lambda.
So it's literally
the difference between the probability of my coin landing on head and or my coin landing on tail.
Right. So here, let me understand. So you consider one density matrix. You consider different, let's say, realizations via purification. So say, like, I consider purification and different ways of measuring the environment that leads to this ensemble. So you're saying different such situations will lead to the same overall statistics, but like different statistical properties, like different momenta or something like that, or?
So yes. So let me be. I can be a bit more precise. It's just that sometimes it's not the right thing to do. So because it confuses. So imagine. Let's move to the classical case for a second. Right? You have two random variables, x and y.
Mm-hmm.
and x is
your system and y is your environment, right? Now let me fix the marginal of x, p of x.
Mm-hmm.
Of course,
I can create the same p of x in a lot of different ways, right? With a lot of conditionals.
Yes.
I just have to
change the globally joint distribution, or if you will, I can also change just the conditional probability distribution while keeping my marginal exactly the same. So this situation is exactly, this is exactly the right interpretation. The density matrix
is the marginal,
while the ensemble, it's more like the conditional.
Right. So the only way to distinguish between different marginals is to have the joint distribution, right? So this is the case here as well.
This is the kind of obvious interpretation, and I would say that it's not the only one. It's certainly the most obvious one. There is a different way to do it, which is, so take this interpretation of the density matrix, right? Mm-hmm. And now imagine that for some reason, you also have access not just to the averages of zi bar and zj, but you have access to the average zi bar, zj, zk bar, zn. Now, suddenly, you become sensitive not just to the average, which is the density matrix, but to higher moments, right? And then the properties of Q, which is the density, become important. Now, this is the moment interpretation, which it's the way people describe random quantum state generators through T designs.
Okay.
And the idea is that if I have, imagine that you have two machines that emit state,
right? I emit
certain states.
I take the average.
I get a certain density matrix. Fine. Now I get a copy of my machine that I put in a tensor product. I emit state, and I take the joint average. That's the second moment.
But average, sorry, what do you mean?
So I mean,
literally doing the average of the tensor product state. Yes.
Okay. Okay. So
instead of
averaging and then tensor producting, you're doing the average of the tensor product.
okay.
then you
Become sensitive to the true, quote unquote, way in which you have generated those pure states, which is the geometric quantum state or the ensemble behind it.
So you're saying if you generate multiple copies of the same state, you can actually access. Okay.
exactly. Right. Yeah. So
ensemble.
Yeah. So
you can.
So this is not
completely worked out. I know for sure that I can access copies of z bar I, zj, which means objects that go like z bar I, zj, z bar k, zn, and then z bar a, zb, and so on and so forth. That can be done by basically tensor producting and taking the joint statistics with these multiple copies of your system. However, is that complete in the geometric sense, in the sense that you can access everything about Q of Z? That I don't know the answer.
Okay.
So it's enough
that you can say, no, you need something beyond the density matrix to characterize that object, and you definitely need Q. However, is Q the minimalistic representation for that?
I don't
have the answer to that. Now, I have a partial answer, which is that when the ensemble has a finite number of components, so it's basically a finite sum of Dirac things, then yes, moments are enough, because it's like when you try to characterize a probability distribution P of X through its moments. If P of X, it's a probability mass over a subset that it's finite, then effectively after a certain number of moments, things are not linearly, they're not independent anymore. And so the moments completely characterize the distribution. You just have to invert the matrix, which is called the van der Monde matrix, and you'll get your probability distribution from the moments. So if it's finite, everything works out. I don't know in the most general case.
Yeah. I mean, there's like hamburger problems, this kind of stuff, no? Yeah, it's complex, okay.
Yeah. So
for me, it's enough to say that properties of Q matter. I don't know if all the properties of Q matter.
Right. Thanks.
People have more questions about this?
If not,
all right. So the point is that you have a notion of quantum state, of a state of a quantum system that depends both on the measurement statistics and on the resources that we use to create that statistics.
So why is it
relevant? So I'm just going to go over. I'm just going to mention a bunch of areas which, whether knowingly or unknowingly, I don't know. I just had to kind of put together this from very different. Well, they're not very different, but from different areas in physics, which don't seem to talk too much with each other. What you're seeing in this diagram is a set of topics where the notion of ensemble is actually the central notion rather than the density matrix. So on the quantum optics sides, you get things like, which especially people in Palermo are very familiar with, like the notions of quantum trajectories and unraveling of the master equation. These are basically, I don't know if they're exactly identical, because there you have a well-defined dynamics, but they're effectively the same thing. And notions like preferred ensemble, they were defined by Weissman and Vaccaro, where they said that if you have an open system that evolves with the Lindbladian, so it's a Markovian thing, the dynamics kind of uniquely selects a preferred ensemble. So while mathematically it's true that all the ensembles are going to be possible, because of the dynamics, that's not entirely true. Now, moving away from quantum optics into, for example, quantum information theory and foundations, you have things like the MIEPT, the measurement induced entanglement phase transition, where if you have a circuit that evolved, a qubit circuit that evolves with joint unitaries, basically you do nearest neighbors unitaries, and then with a certain probability after a unitary, you perform a local measurement. Then depending on the rate at which you measure, you either get something that is localized, so you produce entanglement at a much lower rate, or you basically don't measure fast enough and you produce the same amount of entanglement that you would produce without making the measurement. Now, this is a phenomenology that it's actually not a phenomenology of the density matrix, because the density matrix kind of goes very quickly to a maximally mixed state. It's actually a phenomenology of the ensemble, and it's a phenomenology that you recognize when you look at the conditional states given the measurement. Then you have things like deep thermalization. There is Weinberg's extension of quantum mechanics into nonlinear quantum mechanics that exploits some of these ideas. And maybe the most obvious one for me is the theory of random state generators, where if you want to really characterize a random quantum state generators, which allegedly should be a very useful routine in a lot of quantum computers, what you need to characterize is not just the density matrix, but truly the probability distribution of pure state that your random quantum state generator can emit. So you would like to characterize an object exactly like the geometric quantum state or the ensemble. So this is just to say that this concept of phenomenology of ensembles are just emerging kind of all over the place, and some of them are older, like quantum trajectories have been around for a long time and they're well established. Some others are more recent, like deep thermalization and measurement-induced entanglement phase transition. But they're the way I see it is that as we move forward in our understanding of open quantum systems, we're kind of probing deeper and deeper layers of how the statistics that we observe from quantum systems are generated by interaction with the environment. How much time do I have?
I guess the answer is how much you need.
I think so, Fabio. I think you can go ahead if you want, but let's say 10-15 minutes. Yeah.
Okay. Yeah. So the main point. So what I've talked about is this is very much like an ongoing research direction, and I've talked about these very general ideas and aspects of things that I'm doing. I haven't been incredibly concrete in terms of how I'm using them and what they're useful for. And so here's just a list of things that I have done and that are currently ongoing. And I just want to focus